When you read a sentence, you intuitively grasp the meaning of the text. But a computer processing raw text sees nothing but a string of meaningless characters. To make a machine understand language, we have to teach it how to read. In natural language processing, we rely on a core linguistic rule. A word's meaning is defined by the company it keeps. We figure out what a token means by looking at the context words surrounding it. If a specific word frequently appears right next to terms like crust, apple, or sugar, the computer begins to build an association. It recognizes that this word behaves a lot like pie. Translating human vocabulary into these measurable context associations is the first step in converting language into machine-readable numbers. This co-occurrence matrix tracks associations. Rows represent target words, columns represent context words, and cells contain raw counts of them appearing together. Observing the row for digital, we see strong ties to computer and data. This entire horizontal sequence forms a sparse embedding vector. It is considered sparse because of the sheer volume of empty space. If we train this model on a real-world vocabulary of 50,000 words, the vast majority of the cells for any given word will be 0. We have successfully turned words into numbers. But relying entirely on raw counts introduces a massive structural weakness into our data. The flaw with raw counting comes down to frequency. Common vocabulary words like the and of appear constantly, meaning they will register massive hit counts across every single row in our matrix. These filler words drown out the meaningful context. When every word has a high co-occurrence with the data blurs and everything starts to look related to everything else. These tables show the results of a mathematical filter called PPMI, or Positive Pointwise Mutual Information. PPMI calculates whether two words appear together more often than we would expect by random chance, rewarding statistically significant co-occurrences while crushing weak connections to 0. This filter cleans the noise out of the matrix, leaving us with highly accurate weights. With reliable numbers in place, our next step is figuring out how to measure the distance between two different word vectors. This graph plots word vectors as physical points in space, allowing us to visually see semantic relationships. Related words group closely, resulting in a narrow angle. Unrelated words point away in different directions. To find the exact angle between any two vectors, we use a formula called Cosine Similarity. We can break this down logically. The top half of the equation is the dot product. It calculates the raw overlap of shared context between the two words, but relying on the dot product alone creates a trap. Frequent words naturally produce longer mathematical vectors, artificially inflating their overlap score. The denominator solves this by dividing by vector lengths. Normalizing the score acts as a mathematical equalizer. Think about how this behaves. If we plot two vectors of completely different lengths, but they point in the exact same direction, what is their similarity score? The answer is 1. Cosine similarity identifies that their context profiles are identical, ignoring how frequently the words actually appear in the text. Even with accurate distance measurements, our matrix still has a major structural limitation regarding synonymy. Because words like car and automobile each have their own separate columns, the computer treats them as unrelated concepts. To solve this, we must compress the data. We need to shrink a massive 50,000 column sparse matrix into a short, dense vector of just a few hundred columns. We achieve this using a linear algebra technique called truncated Singular Value Decomposition, or SVD. SVD acts like an object casting a shadow, discarding the least important data variations. This forces similar concepts, like synonyms, to merge into the same hidden mathematical dimensions. This compression yields a dense embedding. It requires fewer parameters, captures overlapping meanings naturally, and prevents the system from overfitting to rigid training data. Dense embeddings organize words into a spatial map, where the model performs literal arithmetic with concepts. If we take the vector for Rome, subtract Italy, and add France, the resulting coordinates land precisely on the point labeled Paris. By mapping relationships mathematically, we give machines a functional geometry of language. This structure powers modern search engines, advanced translation tools, and large language models. To summarize, we use sparse embeddings to count associations, SVD compression to build efficient, dense embeddings, and cosine similarity to measure the distance between them. Converting letters into numbers builds the mathematical universe of meaning necessary for advanced neural networks to process our world.